The first lecture for this unit is going to cover density and types of heat transfer. Hopefully a lot of this sounds familiar to you guys from 6th grade science. So the first concept we're going to look at is density. And density is the amount of matter compared to the volume it occupies. So if you look at this image here, we have the same volume, the same square moving up, and yet we have more and more smiley faces as we move towards the solid phase. The solid phase is more dense because you have more matter per volume. So if we're looking at an object that has low density, the atoms are going to be spread really far apart from each other relative to the volume that's enclosing it. Whereas if an object has high density, the atoms are going to be really close together and tightly packed into that same volume. Mathematically, when we're trying to solve for density, the equation is mass divided by volume, which means that density is equal to the amount of matter divided by the space it occupies. And depending on the type of material you have, they can have different densities because different kinds of atoms are going to line up differently. So for example, if you have the same volume size piece of silver compared to the same volume of, say, a piece of ice, they're going to have very different densities because they are made of different atoms and the atoms are going to align differently. This is a video that you can watch on density in the slide deck that's not the recording if you want more information. So if we're going to do one quick mathematical example for solving density type equations, let's look at this one. Density equals mass divided by volume. And in this particular word problem, we're given the substance density to be 5.6 grams per milliliter. So we're given the density and asked to solve for mass. So you set your equation up like this, and then using simple algebraic functions, you're going to multiply the 25 milliliters times 5.6 grams per milliliters to get the mass. Your milliliters will cancel and you're left with 140 grams is your mass for this given example. When we're looking at heat transfer is going to involve the movement of heat, right? And heat is always going to move from a warmer place to a cooler place. When an object is undergoing any sort of heat transfer, the object is ultimately going to adjust to the temperature of their surroundings. So if you have a hot object in a cool room, that hotter object is going to cool to room temperature. Think of a hot pan you just took off a stove. If you leave it sitting on the cool stove top, eventually it will cool to room temperature and you're going to be able to touch it to clean it. On the other hand, cold objects in a warmer room are going to heat up to room temperature. So if you had like a bottle of water in the fridge where it was cold and then you set it out on your kitchen counter, eventually the liquid in that bottle is going to heat up to room temperature. That's an example of heat transfer. So here's a little situation. If you have a cup of coffee and a red popsicle left on the table in this room, what would happen to them and why? One is a hot substance, one is a cold substance. So the cup of coffee is going to cool until it reaches room temperature, whereas the popsicle is going to melt and the liquid from that red popsicle is going to warm up until it reaches room temperature. Heat can transfer itself in 3 different ways. We're going to look at conduction, convection, and radiation. But regardless of the method in which heat is transferring, heat is still always moving from hot to cold. Let's look at convection. Convection is going to be the flow of currents in a liquid or a gas. And when you get these currents when you actually heat up a material. And what this is going to do is it's going to cause the warmer, less dense material to rise, and then the cooler, more dense material is going to sink. So look at this pot heating up. Boiling a pot of water is a classic example of convection inside the water itself. So as the water heats up down below, it's going to rise to the surface, and the cooler water up top is going to sink to the bottom because it's more dense. And you get this rising and sinking motion that is called a convection current. So convection again, heat rises. As it rises, it's going to cool. Cooler air is more dense, it's going to sink, and you get this continual circular motion. Hot, less dense material rises. Cool, more dense material sinks. So here are just some everyday examples of convection currents that go on. We have in the top left the global ocean currents. We have warm and cold currents. If you look over down here, if you have just simply a heater in a house, heat rises. If you sleep on the top bunk bed, you're well aware of this phenomenon. And the cool air sinks. Let's look over here. We have inside the Earth's mantle. We're going to be looking at this. We have convection currents going on. Hot material is going to heat up in the core and it's going to rise to the surface. And this is ultimately going to lead us into plate tectonics and the movement of the crust on the Earth's surface. So there's lots of different real life examples, and we've talked about the boiling water and all of that type of food cooking stuff. So when we're talking about convection on Earth, remember this is on top of Earth. The first question I put there is Earth's surface equally heated by the sun? And the answer is no. Think about it. The Earth is a round ball. So if you're shining a light on that round ball, it is not going to heat up equally. So where is Earth heated the most? Along the equator, the widest part of the Earth's surface. And where is it heated the least? That would be the poles. So if you look at this image here, look at the solar radiation coming in and heating the Earth's surface. There's unequal heating going on. And whenever you have unequal heating, you're going to have the creation of convection currents because some places are going to be hotter, so air is going to rise faster, and some areas are going to be cooler and air will not be rising as fast. So what happens here, let's get this all up, is we create these little convection currents all around the Earth's surface. And those convection currents in air are ultimately what we call wind. So wind is just the movement of air from different areas of density, essentially due to temperature differences. Hot, moist air is going to rise because it's hot. So look along the equator. This hot, moist air is going to move out and it's going to move away from it's going to rise up, and then as it cools down, it's going to sink again because now it's more dense, and it's going to continually create these little convection currents all around the surface of Earth. Now, if we go inside the Earth's surface, you're going to see convection cells occurring underneath the crust in the mantle. So as you're moving towards the center of the Earth to its core, the temperature is going to increase dramatically, whereas the outside of the crust is a lot cooler. And so this heat rising from the inside, moving towards the Earth's crust and cooling and then circulating back down are going to create convection cells within the Earth's mantle, kind of that layer right under the crust. And this is another example of convection going on inside the Earth. So what does this do to the Earth's surface? Well, it creates a lot of different geographical features and phenomenon, including earthquakes. That's where we live, right here in California, plates sliding by each other due to the mantle moving underneath. We have mountain building when plates collide with one another. Volcanoes is where lava, magma from inside the Earth is going to bubble up. And we have trenches, which you can see here. You have an ocean trench right here in the middle. That's going to be where two plates are diverging from one another. We have a big trench right off our coast here in Monterey. So here in California, we're pretty unique geographically in that we have all four of these features taking place close by. Here's another image of it, and you might have learned about something like this in your earth science class or somewhere else, but these are all the features that form due to convection going on underneath the Earth's surface in the mantle. Now, the second type of heat transfer is called conduction. Now, conduction is going to be heat transfer through direct contact. So that's the key thing, direct contact. Particles are physically colliding with one another. And now conduction occurs more easily in solids than it does in liquids. I think we've all been victim of this little animation where you touch the handle of something that's too hot. That is conduction. Heat is going from the hot handle to your hand very quickly. So why is conduction easier in solids than liquids? Well, it has to do with how close the atoms and molecules are together in solids. In solids, your atoms and molecules are very, very tightly compact, and so they only have a very short distance for the heat to transfer from one atom to the next. As they transfer from one atom to next, that's your energy transfer, and it's going to quickly heat up whatever is touching it. So remember, conduction involves direct contact. Have you ever held ice in your hand? You are undergoing conduction. So the faster moving molecules in your hand are actually bumping against the slow moving molecules in the ice, and therefore over time the ice is going to melt. And depending how warm your hand is will determine how quickly the ice actually melts. But since that is direct contact, that is conduction, not convection. Now, our last example of heat transfer is radiation. And radiation is the transfer of heat through space by some sort of electromagnetic wave. So if you look at the image there, you see the sun. That's our classic example of heat transfer due to radiation. So this is different than conduction and convection because it occurs in empty space, but it can also occur in solids, liquids, and gases. So there's different types of wavelengths that emit radiation. We know visible light, infrared, UV. Not all of them are visible to our eyes, but they are in fact occurring. So some radiation examples in real life: standing by a campfire, your marshmallows getting toasted. You can see the sun heats up the house. You can feel it if you're in your room on your bed, laying down and the sun comes through the window. We have microwaves. How about heat lamps keeping food warm at buffets back when we were allowed to go out to eat? These are all different types of radiation examples. And notice there's no direct contact. These are all waves emitting energy through empty space. So in conclusion, the three types of heat transfer methods we talked about were convection, conduction, and radiation. And oftentimes they go together. So I like these little images because they kind of show all three going on at once. So in a house, you have radiation from the sun heating up the walls. You have conduction occurring with the direct contact in the walls themselves. And then you have convection currents occurring inside the house due to hot air rising and cold air sinking. What about conduction and convection in a pot? Well, the conduction is the heating mechanism actually touching your pot. So that would be conduction. And then inside whatever the water is or liquid, convection is going to start occurring. And so these are your three heat transfer methods. If you want, you can visit the slide deck and there are more examples and questions and animations for you to watch on your own time. Hope that helped.